It's a real pleasure today to introduce Professor Andreas Michael. And Andreas is an assistant professor at the University of North Dakota, and he's been there since 2023. He also serves as the faculty advisor for the local student chapter of the SPE. And his research interests are across all petroleum engineering subdisciplines. And as you can see from the flyer, he is well published and engaged in all aspects of petroleum engineering. He's points out that he's a Greek Cypriot, and he's been in the country, the United States, since 2010. He holds a bachelor's and master's degree from the University of Texas at Austin and a doctorate from Louisiana State University, and those are in petroleum engineering. And his PhD dissertation was entitled Fluid-Driven Fracture Initiation from Oil and Gas Wells, Considering Lifetime Stresses. And that received LSU's Distinguished Dissertation of the Year award for STEM in 2020. And in 2020-2021, he served as a managing editor of The Way Ahead, which is SPE's magazine for young professionals. So a real pleasure today to introduce Andreas Michael. Thank you. Andreas.
Thank you, Dr. McLennan, for the invitation. And can you see my screen?
We can, and it's full screen.
Oh, nice, nice. Thank you also to Igor for arranging this, and I'm very happy to be able to give this presentation. And I'm also very happy to see the growing hydraulic fracturing community within ARMA. The title of my presentation is How to Engineer Transverse Hydraulic Fractures from Horizontal Wells in Reverse Faulting Stressed Environments. That's a pretty important topic in geomechanics in general. So before I dive into the technical stuff, a little bit of what I do here in UND. I have been in this position since 2023. Normally, in the fall semesters, I teach two classes, drilling engineering and geomechanics. In one of those geomechanics lectures last fall is when I came up with this idea, actually. Richard Schultz is teaching this class this semester. And in the spring, I generally teach advanced drilling engineering and well completions, which is a class that is coupled with advanced stimulation techniques, which is a purely graduate course. Generally speaking, undergraduates will go through the stream of those classes as they will take drilling in the fall semester of their junior year, advanced drilling in the spring semester, and then geomechanics in the fall semester of their senior year, and then they will finish with well completions. So each class is a prerequisite of the previous one. Now, as you know, I'm teaching a lot of drilling courses, and UND has a very big portion of its student population that is online students. So I make a very big use of Drilling Simulator 3, which is an iPhone app, actually. And we have, it's a very practical teaching tool, especially for online students. We use it to run class exercises and assign projects. And we can also use it for research purposes, although I have not yet engaged into that. And it represents a proper utilization of digital transformation. And you can find a lot of the exercises that I cover in class. I have them on YouTube with step-by-step guides. Now, in terms of research projects, I actually have 6 projects going. One of those projects, I'm running it by myself completely. And then I have a student who's a dual master student and PhD, so he's running 2 projects at the same time. And 3 purely PhD students. I have a project on underground blowout prevention from offshore wells. I have a project on experimental investigation on hydraulic fracture interference using laboratory scale testing on transparent gelatin blocks. I have a project on mechanistic modeling on well integrity. We have a project on formation damage mitigation in enhanced oil recovery operations in carbonate formations. And we have a thermohydroporomechanical modeling projects for hydraulic fracture initiation. What I will talk today, the project I am going to be discussing today involves project number 2 and a little bit from project number 5. Project number 2 is the one that is run by the student who is a dual master's and a PhD student. And it has been presented as a paper in the last ARMA symposium in Santa Fe. And I did present it. I was the first author on the paper. And then second author was Chukwuemeka Kalu, and then third author was Abdelmalek Abbes. It's basically gonna be, the goal is for that to be Chukwuemeka Kalu's master's project. So it's gonna become eventually his master's thesis. So he's gonna take the lead on this project, and we plan on submitting a paper for peer review soon, somewhere in the Elsevier journals. Now, a little bit of a historical overview in hydraulic fracturing. I always try to bring history into topics I'm discussing. Is if we go back to the mid-1800s, people were torpedoing wells for stimulation purposes. And oil was discovered in the US in 1859. And if we go a few years later, this gentleman here is actually the guy who assassinated Abraham Lincoln, John Wilkes Booth. He was an actor, but his job before that was to torpedo wells for stimulation purposes. He was running a company called Dramatic Oil because he liked acting, I guess. And it was a common practice to torpedo wells in order to stimulate production. Now, in 1929, there was the first horizontal well drilled in Texon, Texas, by somebody called Robert E. Lee, not to be confused with the Confederate general. I think the patent for horizontal wells existed from the 1890s, but the first horizontal well was in 1929. And then in 1957, it's the first time fluid was used for stimulation purposes in Hugoton Field in Kansas. Napalm was used, and then 2 years after that, in 1949, we had the first commercial treatment. Now, in 1982, George Mitchell drilled the first well in Barnett Shale in Texas. And I think it was 1997 when the first slick water fracture treatment was performed. And it basically brought hydraulic fracturing technology to more or less where it stands today. So when we do modern day hydraulic fracture treatments, our goal is we want something that looks more or less like you come in with a well, you drill a vertical section followed by a horizontal lateral. Now, in real life, the things will look a little bit more gentle. It won't be like an abrupt kink. You have a kickoff point and then the landing point, but then you have the horizontal lateral through a shale section. And then you go from the toe of the lateral to the heel of the lateral, trying to pump as many fractures as you can. And you want to stack them next to each other, and you want to get as many as you can next to each other. So the goal is what we call a transverse hydraulic fracture, which I have here colored with blue. It's a fracture that is orthogonally oriented to the wellbore. if you have a horizontal wellbore, as in this case, it would be also called a vertical fracture. But the name transverse has to do with the way it's aligned to the wellbore. Some call it lateral fractures, some call it orthogonal fractures, etc., etc. And sometimes you may not be able to get a transverse fracture like that. You might get something like the red fracture on the left, oops, sorry, which is basically a longitudinal fracture. It's a fracture oriented axially with respect to the wellbore. Now, the productivity of one longitudinal fracture is higher than that of one transverse fracture. However, if you stack many transverse fractures next to each other, they will outperform one gigantic longitudinal fracture, which would be what you will get if you get multiple longitudinal fractures growing next to each other. So one longitudinal fracture outperforms the transverse, but many transverse will outdo a gigantic longitudinal fracture. So the goal, what we are going after in modern day hydraulic fracture treatments, is the blue fracture on the right. Now, many times, I guess the general rule of thumb is that if you drill your horizontal lateral along the least compressive stress, you maximize your chances to get transverse fracture initiation. But this is not always the case, and that is because when you are drilling a well, you are removing rock and you are replacing it with fluid. That disturbs the stress field around it. And you also do other stuff like you run casing, you cement it in place, you have formation damage coming from different ways. So you have a lot of stress impediments in the near wellbore region that may prevent your fractures from initiating in this favorable direction. And I have here on the left a screenshot from Valco and Economides' book, Hydraulic Fracture Mechanics, from 1995. And you see a well that was drilled in a favorable direction, but the initiation wasn't favorable. So you get longitudinal fracture initiation from that well. And these longitudinal fractures won't go very far into far away from the well. They will either terminate prematurely or they will hit on a discontinuity like a pre-existing fault, and they will reorient to the favorable transverse orientation. Nevertheless, this twisting that takes place in the near wellbore region creates what we call near wellbore fracture tortuosity, and it affects operations quite greatly in an adverse fashion. You can get early screenouts or low stimulated well productivity, which is, it affects your economics very badly. Now, on the picture on the right, you have a more real-world version of what happens in a larger scale, let's say, and that is from Barry and Miskimin's 2015. You have longitudinal components mixing with transverse components, causing a lot of what we call near wellbore tortuosity, and we are trying to avoid this. And from the same paper, I have here a picture from a tracer test run during the treatment, a multi-stage treatment, where the fluid used to stimulate stage 1 is colored yellow. The fluid used to stimulate stage 2 is colored red, and the fluid used to stimulate stage 3 is colored blue. So if we do our job right, yellow fluid will stay in stage 1, red fluid will stay in stage 2, blue fluid will stay in stage 3. But you see mixing, you see yellow fluid in stage 2 and 3, red fluid in stage 1 and 3, and blue fluid in stage 1 and 2. So you get stage communication, which was attributed mainly to those longitudinal fracture initiations in that paper. And it shows us that longitudinal fracture initiation is a reality many times, and it can adversely impact your stimulation treatment result. So we want to avoid that. Now, Igor Dontsov last year had a very, very interesting blog for ResFrac where he presented a lot of evidence in terms of microseismic data, core observation, casing deformation, tilt meter data, and even fiber optic measurements that basically provided evidence for horizontal fractures, which would be basically what we call longitudinal fractures from a horizontal well. And this year, he had another interesting blog where he discussed the computational modeling of those horizontal fractures, which is very, very important. So slowly but surely, these longitudinal fracture initiations become more and more important in our job. And it's something, I guess, that is worth examining. And to examine fracture initiation, you have to look at the subsurface stress state, which is simplified greatly by the Andersonian folding theory, where we have basically a vertical stress called SV and a horizontal stress SH max and SH min. SH max always bigger or equal to SH min. And notice the uppercase H for SH max. So the two rules that we have to honor for Andersonian's theory is basically one of the stresses needs to be vertical, the other two need to be horizontal, and SH max cannot be smaller than SH min. Now, that gives an infinite number of different stress permutations for those three in situ principal stresses. We need to think which of those permutations will yield a stable environment. And for that, we need to consider fault stability. And we basically use a stress polygon to display this. I know that it was Zopak sometime in the 70s, I think, or early 80s that came up with the concept of a stress polygon. The version I'm using in my work, in my publications, is one that was from Nelson in 2005, which is fully dimensionless. So we have SH max on the vertical axis and SH min on the horizontal axis, both normalized by SV. The dotted diagonal represents the line of horizontal isotropy where SH max is equal to SH min. As we cannot have SH min bigger than SH max, anything below that diagonal is impossible to exist. And then with the solid lines, we have the friction limits. That is basically honoring Moore Coulomb's failure criterion for pre-existing faults who have exhibit friction factor of mu between 0.6 and 0.8. The solid lines are for 0.6 and the thinner solid lines are for 0.8. Barley in 1978, I believe he was working for USGS. He did a lot of experiments on big blocks of rock, and he arrived to the conclusion that mu for pre-existing faults is between 0.6 and 0.8. So any stress state outside those bounds will be rendered unstable. That means if you have a fault existing in this under this stress state, it will automatically fail in shear. There will be basically an earthquake, which makes it unstable. Now, there is a lot of assumptions associated with this polygon. All the faults need to be critically stressed and favorably oriented. But that basically gives you a nice idea of what stress states are possible to exist in a stable fashion in the Earth's subsurface. And we have the three faulting stress regimes: normal, strike slip, and reverse. Reverse faulting has SH max bigger than SH mean, which is bigger than SV. And something that was counterintuitive when I was young and I was working on this stuff as a student was that even though normal faulting is the most common stress regime that you will encounter in the Earth's subsurface, the range of stable stress states that are possible to exist for reverse faulting is massively outweighs those of strike slip and normal faulting. So that's an interesting, I guess, finding. Now, when it comes to tectonic confinement, the limits basically of SH max and SH mean, Simpson tried to further simplify everything in 1997 by lumping the three values of the in-situ stress states into one dimensionless variable. He called that A phi, which basically varies from 0 to 3. 0 to 1 is for normal faulting, 1 to 2 is for strike slip faulting, and 2 to 3 is for reverse faulting. And Jens-Erik Lundsny, he was in Stanford at the time. He thought about applying a temperature color scale into those A phi range. So dark blue was assigned to very strong normal faulting, dark red was assigned to very strong reverse faulting, and then everything else designated with intermediate coloring. The same scientist with Zopak in 2022, they came up with a plot that has normalized stress on the vertical axis and A phi on the horizontal axis, and shows how the limits of the SH max and SH mean are given for each regime, each A phi value. Now you will notice we are interested into this little sliver on the right, which is the reverse faulting stress state for this presentation. You will see that there is quite a bit of range from SH max to SH mean for that stress regime. And in my geomechanics class, I make the students for one homework draw this diagram because I do believe that it has a lot of utility. If we are able to show failure on this plot in a graphic manner, it will become a very, very valuable tool, almost as strong as a stress polygon is today, actually. So looking at the map of North America, we see a lot of reverse faulting stress environments on the East Coast. And then also in the west side of Canada, where Montney Shale is, we see, and there is parts in Mexico as well, in the south, etc. But the application of what I'm discussing in this project extends beyond reverse faulting stress states. There is areas of Vaca Muerta that is strike slip towards reverse faulting that have the same issue. Utica, Montney Shale, it has parts that are reverse faulting. The Cooper Basin in Australia, Gippsland Basin in Australia, also parts of Sichuan Basin in China, they all had the same issue that this project is trying to address. So I guess there is a lot of utility that goes beyond reverse faulting stress states. Now, if we are giving this presentation in the 1950s, well, it wouldn't be via Zoom, and the room would be divided between horizontals and verticals. There will be people advocating that all fractures are vertical, and other people advocating that all fractures are horizontal, and they will both have strong supporting evidence on either side. And it was Hubbard and Willis in 1957 that sort of ended the discussion by saying that tensile fractures can be either horizontal or vertical. It depends on the stress state. And generally, or always, fractures, mode 1 tensile fractures, often doing work against the least compressive in situ stress. Now, for normal faulting and strike slip faulting, this is easy. As I said earlier, you just aim your lateral to be parallel to SH mean, and then you maximize your chances for a favorable transverse fracture initiation. Sometimes this may not be the case, but still, it doesn't mean that you have to drill your well any different than that. In fact, in Louisiana, it's a state law to drill your well north to south. So that's basically towards the Gulf. That's where basically the approximate direction of SH mean in that area. But when you are dealing with a reverse faulting stress state, the least compressive stress is basically SV. So that will promote those longitudinal pancake-like fractures, which we want to avoid because we don't want our stimulated well to be underproducing. So I got the idea based on two patents. The first of them is one that was published the year I was born, actually, in 1989. And it was a bunch of people working in California. They were trying to fracture zones under diatomite formations. And diatomite is basically chirilliter. It's very light, has very, very low density. So it doesn't weigh a lot. It doesn't add a lot to the overburden stress. So they were trying to get longitudinal fractures from those vertical wells, and they were getting transverse fractures. And that was a problem. So what they decided to do was to create a transverse fracture and use the stress shadows from that fracture to increase the vertical stress, the overburden stress below it. So when you go underneath this transverse fracture and you try to initiate a fracture from underneath, it will be longitudinal. And then you hope that this longitudinal fracture you will propagate long enough and dominate production so that it will be your well won't be underperforming. And they were very successful in that venture, and they published a patent about it. And I think one of those authors of the patent, he came to LSU to give us a presentation on artificial lift back in 2018, and I had a discussion with him afterwards in the Q&A. And he mentioned this patent to me, but I didn't know specifics about it. And it was last January where I remember his name. I reached out to him, and he sent me the patent, and I saw that this is the method they actually used. And the second, so they go with a transverse on top, followed by a longitudinal right at the bottom. And the second patent that is related to it is it's a more modern one from 2012. It's the Texas two-step, which basically suggests that if you go for an alternative fracture sequence instead of a consecutive traditional one, instead of going straight consecutively 1, 2, 3, 4, 5, you jump one stage and then you go backwards. The stress shadow will, some adverse stress shadow effects will be mitigated, so the resultant geometric profile of the produced fractures will be much more favorable. So I thought about, my hypothesis was that if we utilize stress shadows from longitudinal fractures initiated beforehand in horizontal wells from reverse faulting stress environment, we will be able to promote transverse, more desirable hydraulic fractures. Because basically, if you look at this first pattern from 89, we are basically dealing with it's the same problem rotated at 90 degrees. They wanted to get a vertical fracture from a vertical well, and we want to get a vertical fracture from basically a horizontal well, or a transverse fracture from a horizontal well. So it's basically the same problem inverted by 90 degrees. To mathematically back our proposed method, we need to look at the stresses on the wellbore walls. We look at two stresses that we are interested about. We look at the red tangential stress indicated by sigma theta theta, and the blue axial stress indicated by sigma xx. Now I color the tangential stress equation with red because that's what drives longitudinal fracture initiation, and I color the axial stress with blue because that's what drives the transverse fracture initiation. And that is in the absence of considerations for perforation, tunnels, etc., etc. You just have the rock penetrated by the horizontal lateral. So in that case, the idea is that you will generate two longitudinal fractures from two stages that are apart from each other by one, and then you are gonna use stress shadowing from those fractures to increase the local overburden stress SV, such that when you go between them and you try to initiate a fracture between them, this fracture will be transverse and will dominate production. Mathematically, at this level of complexity, the problem is exactly the same as that of drilling induced tensile fractures. So basically, you have two criteria that you need to satisfy, two mathematical criteria that you need to satisfy so that you get transverse fracture initiation. The first is that you want your axial stress, the blue axial stress, to be more tensile than the tensile strength of the rock. And two, you want it to be more tensile than the tangential stress at that location, the red tangential stress. And then you can basically play with math algebraically and derive closed form expressions of the criteria you need to satisfy for this method to work. And even then, even beyond that, you can also attempt to derive closed form expressions for the fracture initiation pressure. And we can also take our analysis one step further and incorporate the presence of the perforation tunnel, which will further increase complexity in the near well vicinity, because the perforation tunnel will also interfere with your stress field in that location. Sadly, there is no, to my knowledge, fully analytical solution for the stresses around the base of the perforation tunnel, where we can assume that the fracture will initiate. It's a very famous mathematical geometric shape known as the Steinmetz curve. And I'm not aware of any mathematical solution for the stress field around that Steinmetz curve. I would be very interested about that, actually. But Hossein in 2000 had the idea that you can approximate the stress in that area by doing a double Kirsch analysis. So you neglect the presence of the perforation and you do a Kirsch analysis for the wellbore walls at that location, and then you use the results from the first Kirsch analysis for a second Kirsch analysis to find the tangential stress on the perforation base. And then from that stress, which I call sigma theta theta int, you can calculate it at two different locations. The location given by the red arrow, denoted by sigma theta L, is the stress you need to overcome to initiate a longitudinal fracture initiation. We call that sigma theta L. And the blue arrow, indicated by sigma theta T, is the stress that you need to overcome to generate transverse fracture initiation. And then basically those two stresses, the red and the blue, they substitute the axial stress and the tangential stress from the analysis in the previous slide for transverse fracture initiation. And you can derive closed form expressions for the approximations of those stresses. Now I have to emphasize that these are approximations, they are not analytical solutions. And I have a student, his name is Nassim Abdallah, that is working specifically on this topic, trying to correct them, provide numerical corrections for those stresses. But another thing that he did in a paper that he published, we presented in ARMA 2024, was that he added thermal effects and linear poroelasticity to those expressions. Hossein, when he derived those expressions, he neglected pore pressure completely, as well as tensile strength. And during my PhD, I modified those expressions for pore pressure, and Nassim further modified those for linear poroelasticity and thermal effects. Now we have the idea, but we don't know how well it can work in real life. So we had to do some validation for scale. For that, we use experimental testing transparent gelatin blocks. At UND, we have a manifold transparent gelatin blocks to basically mimic three-stage fracture treatment from an imaginary horizontal well going through. This is how a manifold looks like in real life. It's fairly simple. But basically we are mimicking three stages, one perforation per stage, generating one fracture per stage. And you can very easily modify this to get more than one fracture per stage if you want more complexity. It's just we are still at academic level with this project, so we are keeping it pretty as simple as we can, because there is a lot of geometric complexity you can get from if you try to generate three hydraulic fractures from a horizontal well, actually. Now, when it comes to gelatin tests, gelatin has been used many times for hydraulic fracture experiments. The first time it has been actually used was in that Hubbard and Willis paper in 1957. He actually did an experiment generating a longitudinal fracture in gelatin and an experiment generating a transverse fracture to prove to people that you can have fractures produced in either of those extreme orientations. And I will say since then, it has been used in about a dozen studies, maybe more. I know that volcanologists, they like to use gelatin for their experiments, and basically geologic dikes are tensile fractures, which is basically the same thing as hydraulic fracture. Now, you can use gelatin over a wide range of conditions, but it doesn't mean that it's gonna scale properly with actual reservoir settings. I have two papers. One that was presented in ARMA symposium in 2022, and then a journal that was published last year in the IJRMMS. And basically, I explore scaling for those gelatin experiments, and it's a long discussion on the paper, which I'm not gonna go over, but we use a method that was conceived by De Pater in 1994, and we have dimensionless groups, and we evaluate those groups at laboratory conditions and at field conditions, and we try to stay as close as possible, have the two as close as possible so that we get good matching, good scaling. And one of my, I guess, the main conclusions of that work was that gelatin can scale sufficiently with rock under specific conditions. So we have to manipulate viscosity, we have to manipulate the concentration of powder that we use in the sample. So it doesn't mean that any gelatin experiment would be properly scaled. So once we got the scaling out of the way, we use a base case where we have 3 longitudinal fractures initiating from in the experiment. So we use consecutive sequencing, 3, 2, 1. So we get one longitudinal fracture, then the second one, and then the third one. And this here is the digital representation of the result that I tried to draw in MATLAB. And we see basically the problem that we have in a reverse faulting stress state, the 3 pancake-like longitudinal fractures that if let to grow further, they will merge with each other and make a gigantic pancake-like fracture that won't yield favorable productivity. Then we tried to tried our method, which is using 3-1-2 sequencing. You have a longitudinal fracture from the third stage, then you jump to the first stage and you get another longitudinal one, and then you go in the middle and you produce this transverse fracture. And you hope that this transverse fracture will be able to dominate production so that you get a favorable, better than the base case result in terms of productivity. And now after that, we said, why don't we try to get a little bit more aggressive with it? How about we try to modify our method a little bit so that we can attempt to get 2 transverse fractures out of the 3 stages, and we only use 1 longitudinal. So Kalu, who is the student who was running those experiments, got used a 2-3-1 sequencing. So he got a longitudinal fracture in the middle first, and then he went to the third stage and got transverse fracture from there, and then went to the first stage and got a transverse fracture from there. So now we have 2 transverse fractures that will dominate production, and that will be even better production gains than what we had on the previous slide. And then an alternative variation of that will be, and that works, it's harder to make it work, but it's possible, is if you go 3-1-2 sequencing, and then you go, you get the longitudinal fracture first, and you make sure it's long enough so that you go to the next one, which would be stage 1, you get a transverse fracture there, and then you get the transverse fracture from the middle one as well. And also bearing in mind that it would be harder to get transverse fracture from the first stage than the second stage. So it might be smart to go 3-1-2 than 3-2-1, basically. And of course, you have to. It won't be you won't be able to get all those embodiments in every different setting. There might be settings where it's marginal, so you can get it easily, but you may have more extreme reverse faulting settings where it's going to be very hard to get a transverse hydraulic fracture. So you may need to be more to do more for that to happen. Now, going forward, and this is a project that is quite in its infancy, there is further laboratory scale testing that we can do to optimize the proposed method. We can incorporate natural fractures and see how that interference looks like. We can try with more hydraulic fractures per stage and see how the intrastage dynamics looks like. We can try to quantify trends empirically and how independent variables influence the result, like fluid viscosity plays a very big role. Also, relaxation times with stress is something that we didn't look in that ARMA paper, but will be very important in this topic. And also, we can look at extreme scenarios where the proposed method will not work. One other option is to try to do something like they do in Canada for steam-assisted gravity drainage and have a well on top of the actual production well and try to get a gigantic longitudinal fracture on top, and then you go underneath with another well and try to get those transverse fractures underneath. That would be a much more costly method, but could bear fruit if the stress environment is highly unfavorable. We can do numerical field scale modeling using computational tools. We can have a theoretical focus analysis where we look at the stress state in those in the area where we think fracture will initiate. And we can have a more application focus aspect where we look at proppant placement, etc., etc. We can also optimize for specific scenarios. I know from discussions I had with YPF people that there is areas of Vaca Muerta that they have this problem, and they are looking into ways to suppress this issue or deal with it. And of course, the $1,000 million question would be if we are able to derive a fully analytical solution for the stresses on the perforation base. That will provide us with an analytical model on how to make this work, and that will prevent us from having to do those approximations that could deviate from the true solution by quite a bit, actually. So in conclusion, we look at a method and means for engineering transverse hydraulic fractures from horizontal wells in reverse faulting stress states, exploiting stress shadowing from longitudinal fractures initiated beforehand. We provided experimental validation from scale laboratory testing using transparent gelatin blocks. And we provided different or demonstrated different embodiments that can yield different results. Even we can get two transverse hydraulic fractures promoted from a single longitudinal hydraulic fracture. And this provides the potential to improve production from underperforming frac jobs. And with that, I would like to acknowledge the North Dakota Industrial Commission that was funding this project at the very beginning. The two students that have been working on this project and doing the hard work in the lab, and of course, Igor and John for providing me with this opportunity to present this work. And with that, thank you very much. I would be happy to answer any questions.
Thanks, Andreas. Very insightful. We do have some questions. The First is from Ali Danashi, and he'd like you to comment on the fact that rocks are usually brittle, gelatin is not. Can you take it from there?
Gelatin actually is quite brittle. It exhibits a tensile strength, at least in the concentrations that we are doing. And there is a paper by Kavanagh in 2013 in tectonophysics, where she did an extensive scaling, kinematic, dynamic scaling of gelatin. And she's a volcanologist in Liverpool, England. She was using basically gelatin to model dikes that are tensile failures. She provided correlations for the fracture toughness of gelatin at different concentrations. So if you use a very low concentration, you won't have much brittleness. But if you use higher concentration, you start developing a setup where it's pretty good, pretty brittle. Now, if you use very high, there is high concentrations of gelatin that it can be used for ballistic purposes even. So it's pretty variable the way gelatin can be used as a polymer actually.
And the next question is from Professor Bazant, but I can't see the image, so maybe we'll just move to the next one. Marek is suggesting that you could do this technology for fracturing in vertical wells, where you could do a horizontal frac at the top and the bottom of pay zone and do a longitudinal fracture in between.
Yeah, I would say that would be a variation of that 1989 patent in a sense, where it's basically the opposite problem of what we have with horizontal wells. You are struggling to get a vertical fracture from a vertical well, and in reverse faulting, in our case, we are struggling to get a horizontal fracture. A vertical fracture from a horizontal well. So I will say, yeah, it's just with shale, you want to drill your lateral, make it long enough to facilitate production. So I will stick to horizontal wells as much as it's possible. But like I said, extreme cases may require a method that is it's more costly, and that will come into play.
Okay, and so the next question is from Zeno Philip, and Zeno is interested in what the dimensions of the transverse fracs are. Does it extend beyond the lateral extent of the horizontal frac, and will reorientation inevitably occur? I added the word inevitably, so I was editorializing. I apologize.
Yeah, I agree that if you go further away from the well, eventually you have a reverse faulting stress state, and the fracture will be forced to either terminate or reorient. I wasn't able to test that in the lab because we are limited to the extent of how big the sample can be. Especially we are using very high concentrations of gelatin. But yeah, that would be an issue as you move away from the wellbore, because then you are basically dealing with SV and SH max and SH mean. So it doesn't really matter. You don't have any other stress interference. You are dealing with the in-situ stresses. So yeah, ultimately, I think that's a problem that will be solved on the operational side of things. I mean, if you want to use that method, you will have to basically make fractures that will improve the production. So yeah, that would be a constraint, and it's a very, very good point.
Yeah, and Martin Rylance,
John, this is Bazant. My video is disabled by the host.
okay. I didn't do it intentionally.
But it's disabled.
Well, yeah. Much I can do.
What's happening?
I didn't disable it.
It is crossed and messages.
So
You
what?
can start video because it's disabled by the host.
Yeah. So what was the message, Zdenek?
My message is that you neglect poromechanical effects. Fracture depends on stress in the solid phase. And there is a stress transfer from fluid to solid, which is important.
Yeah, in the paper I mentioned from 2024 with the other student, Nasim Abdallah, he modified those expressions that we have. Let's see, the expressions that we have, where was it? Here, those two, he modified them to include poroelasticity, linear poroelasticity, and thermal effects as well. So you can find more complexity on that paper in regards to poroelasticity, not a lot of complexity, but because we are doing experiments on gelatin and gelatin doesn't have a
No, gelatin not, I mean rock.
Oh yeah, in rock, yeah, you will have to have poroelasticity and pore pressures and yeah, so
In our opinion, it's significant in shape, for example.
yeah, actually, if we consider the approximation, and I'm not saying that the approximation is doing an excellent job or even good enough job, you will see that the poroelastic effects did not make a very big impact for this kind of problems. But in real life, you may have big issues from poroelasticity.
Well, the stresses in the porous phase are significant and then change from full pressure of opening the crack to very low value.
Yeah, and
So,
actually,
we have a different conclusion.
Yeah. So Zdenek, I think Andreas agrees with you, and
Okay.
something that just needs to be considered for sure. Martin Rylance, Martin, do you want to just pose your question?
Hello.
This is Dawn. Hi, this is Dawn calling
Yeah.
from Dr. Phillips' office, returning your call. Oh, okay. I would like to make it.
So let me just, yeah, okay. Martin Rylance observes that in many cases, longitudinal fractures are not horizontal. And do you want to comment on that?
well, yeah, I personally had a problem with the name horizontal and vertical because the wells are not always oriented the same. So it used to be from back on the 50s and 40s when they were drilling vertical wells, and vertical fracture meant longitudinal for vertical well. But for now, a vertical fracture for us is from a horizontal lateral will be transverse. So I prefer using the terms longitudinal and transverse because that's with respect to the orientation of the wellbore always. So it doesn't matter if you are vertical or horizontal. Now, the question was that vertical fractures are not always.
You can have vertical longitudinal fractures.
Yes, and I believe he means about what we see here on the left, the longitudinal fracture initiation. So it's standing. Yeah, that is possible. That is possible. But in both cases, they are longitudinal, axial with respect to the wellbore. And it's what we are trying to avoid, basically, from a horizontal well.
And so we've only got time for one more question. So I'm going to have to, we'll give Mike Smith the last word. And I lost Mike's question. So Mike, are you still there? Do you want to ask the question? Okay.
Turn on my audio there.
There you go.
I was just interested in how do you run the experiment? So you're injecting into fracture one and creating this horizontal fracture. And then you quit injection. Do you then seal off that fracture so you maintain the pressurized fracture? You maintain a width in the fracture while you do your subsequent injections?
Yeah, that's a very, very important question, actually. The way the manifold is designed and we are in the process of further developing it, we are able to hold some back pressure, and of course that can influence the results. But and we see how we can scale that with real life experiments, because you want to be able to hold pressure, or somehow you need to probe the fractures. So yeah, we are able, basically the manifold is injecting from the same fluid source, but through 3 different avenues. So you are able to basically close one route if you want, and then use the other 2, or you can even inject from 2 stages at the same time if you want. So we have this flexibility with the manifold.
Yeah.
But yeah, and you know, an actual reservoir, you'd have leak off, fluid loss, and so if you didn't include proppant, that fracture would close and the stress alteration would disappear.
Yeah, the absence of leak-off in gelatin experiments was explored in that scaling paper I mentioned from 2024, because we have to adjust the volumes in those experiments, because in gelatin you don't have any leak-off, so you are not going to lose any fluid. But in real life, you are going to lose the fluid, so you need to adjust for the 2. And I elaborate a little bit on that journal paper in terms of scaling, and we try to make it fair as much as we can. It is not very easy, I agree. It can be challenging and can lead to misleading results as well. But the principle is pretty much the same. You are going to use stress shadowing from, you have to keep the fractures open, the longitudinal ones. So when you go in between them, you need to get the transverse. So you need to have stress shadowing from the longitudinal fractures, so that you can increase SV between them, and then you are able to generate the transverse.
Okay, thank you.
Thank you, sir.
Yeah, well, we got a bunch more questions. I will pass these on to Professor Michael, and he can get some answers back to you folks. But very interesting, very interesting, and greatly appreciated. Well said. And so thank you, and we'll see everyone probably back at a regular time of 9 a.m. Central in a couple of weeks.
Thank you, everyone.
Yeah, Andreas, that was excellent.
Thank you. Will I be able to see the questions that they were asked?
If we're lucky.
Yeah.
It depends on whether I managed to